Okay, last but not least, I'd like to prove the other direction of the theorem. It's a rough start. And the other direction of the theorem is saying that if I have some regular language, then it can be described by a regular expression. And the idea of this direction of the proof is that I'm going to create a conversion algorithm that starts from any FA, because I know by definition and by theorem that if I have a regular language, it's accepted by some DFA or some NFA or some NFA with epsilon transition. So I create some algorithm which takes any FA and converts it to an equivalent regular expression. So before I give you the steps of this algorithm, and actually the steps I'm going to give you here aren't all that rigorous, I guess I could say. And that's because I don't think it's all that helpful to just show you the steps of the algorithm. I'll post an extra note where I detail exactly what you need to do. And I give a slightly more complicated example. But again, I'll say this again in the video. I said this during the lecture. I'm not going to ask you either on the midterm or on the final to mindlessly go through some algorithm to solve a question. So that's never going to be a question in the midterm or the final, maybe in the assignment, but I don't think those are interesting, and I'm sure you find them very painful and very boring. So, okay, what was I saying? Right. And so then what I want to do is I just want to sort of give you the high-level ideas, the paintbrush strokes of this algorithm. And the first thing I want to do is I want to show you what the goal of the algorithm is. So of course, the goal of the algorithm is to output an equivalent regular expression, but it has a slightly more informative goal, or a slightly more informative sub-goal, and that's that it's to shrink any FA that is given as input, such that the shrunk FA looks like the following GFA. So this is a new type of machine, a generalized finite automata, and the characteristics of GFAs are that they typically have, well, not typically, they have one start state, they have one final state or one accept state. So you know what, I should really write accept because that's what I've been saying so far. And the other feature of GFAs is that as labels to their edges, the labels of edges are regular expressions. And so what that means, what the GFA is then saying, if its label is a regular expression, it's saying that to get from one state to another, a string must match the pattern in the regular expression. Okay. So I'm actually going to rewrite this. I'm going to re-explain this here, so I'm not quite sure why I wrote it, but whatever. So the goal of the algorithm is to create a GFA, where the GFA looks like the following. I have my single start state and my single accept state, and I have a single directed edge going from S to F with label R. And so at this point, it's obvious that the equivalent regular expression of n prime, this is GFA, but we'll see also of n, of the original input FA, is R, right? Clearly, if I have a regular expression that's labeling this edge, and it has a single start state, and to get to the final state, it has to go through this edge, then of course, the equivalent regular expression is just going to be taking the label of the edge and placing that as the regular expression. So that's exactly what I've written down in this example here. Okay. So slightly more formally, this algorithm has two major steps. The first step is taking an FAN and converting it to a GFAN prime. To do that, you need to have a single start state with only outgoing edges, a single accept state with only incoming edges, and like I also said, the feature of the GFA is that the edge labels are regular expressions. So for instance, if in this case I have as an input an NFA, which looks like this, then I can create a GFA which has a single start state and a single accept state. How do I do that? Well, I use epsilon transitions. So I say, this is my new start state, and then for free, I can get to the original start state of the machine. If there were more than one start states, I would just do something like this, right? And then for making a single accept state, I add this state here, I make it an accept state, and I take every original accept state and link it with an epsilon transition to this single accept state. So if I had multiple accept states in my original machine n, for instance I had 3, then I would just link them with epsilon transitions. Because for free I can go from here to here, so I'm not adding nor am I losing any information by doing this. The last thing is that now the labels of my edges are regular expressions. So this already is a regular expression, but a comma b isn't. The equivalent regular expression to this label is a or b, right? Because to get from here to here, I have to have a string which either matches a or b, right? And that's exactly what I've written here. Now the second step of the algorithm is the actual shrinking. And I've given a very sort of high-level intuitive idea of what the shrinking is. Like I said before, I'll give more concrete steps in a note. But essentially what you need to do is you need to rip out all the intermediate states, so all the states except for the start state and the final state, until you get something like this. And when you rip out an intermediate state, you need to stitch the machine back up such that it doesn't lose any information. So for instance, if we take the example that we had here, and we put it back here, and we run through this procedure, let's suppose that I rip out this state. Well, if I rip out this state, I have to stitch back the machine such that the information flowing through that state is preserved. In this case, that information was that to get from this state to that state, I could go through this state by reading an epsilon, then any number of a's, then an a or a b. And so that means that I have as the equivalent label on this directed edge with a smaller number of states, with actually that state ripped out, the regular expression a star a or b. Of course, I could also say that I have epsilon, but having epsilon at the beginning of a regular expression doesn't say anything, right? Doesn't really help me out. And so I can just drop that. Okay. Again, I can do the same thing. I can say, well, now I have this other intermediate state. I want to preserve all the information that flows through it. The information that flows through it is that if I have a string which has as its first part a string that matches this, then as its second part a string that matches any number of b's, and as its last part a string that matches the empty string, or that matches the epsilon regular expression, then it can get from the start state to the accept state. And so then I can just rewrite that without this state. So I rip out this state and I stitch it back up by dropping that state and connecting the start state to the final state using this directed edge with label a star, a or b, b star, and that comes from this part, which is here, then the b star, which comes from any number of b's in the self loop, and then, like I did before, technically there's an epsilon here, but that doesn't add anything to my regular expression, so I can just drop it. Right, so tacitly what I'm assuming is that I'm assuming you can see why if I have a regular expression r, this is equivalent to r concat epsilon, and equivalently epsilon concat r, or r1. Okay, so if you don't see why, just work this out using the languages described by each of these regular expressions, and it should become fairly clear. Okay, and so we've reached the goal that we wanted to. We have the single start state and the single accept state, and we have a single directed edge. So now the equivalent regular expression, I'm just going to take it and I'm going to copy it down here. And now let's see if the regular expression that I created matches the intuition of the mechanics of the machine, the original machine I started with. So here this regular expression is saying I have any number of a's, then I either have an a or b, and then I have any number of b's. Well, let's see if that matches a computation of this NFA-n. I intake some string into this machine, I read any number of a's, then I transition with either a or b, and then I can either stop or read any number of b's. So that logic exactly maps back to what I'd written down here. Okay. So during the lecture, I had given another example here where actually I had made a typo, so I fixed the typo since then. But I think what I'll do is in the note I'll post, I'll think of a better example and I'll work out step by step how you can sort of shrink the machine, because this is of course a simplified case. But for instance, what happens if you have more than a single final state and more than a single start state? So we'll deal with that in a more complicated example that I'll type up. Okay.